Hi, I'm Paul Hewitt, the author of Conceptual Physics. You know, physics is the study of nature, the way things connect to one another. And these connections are underlined by the concepts which are beautifully expressed mathematically. But the focus of conceptual physics will be the beauty of these concepts in English. The equations of physics will be seen as guides to thinking, much more than recipes for numerical problem solving. So the idea is the comprehension of concepts first, and then computations later. Ideally in the laboratory, where they're really meaningful. This tape you're looking at right now is the first. It's the intro of a series of more than 30 tapes. And this is a long step from where I started video in my classes. That's like back in 1974. Let's take a look at my class as it looked like in 1974. Enjoy.
Matt, you want to come up here and try this? Could I have one other volunteer, please, to pick up the anvil and put it on my head? Yeah, chest. It's right here. No, right, yeah, right over here. Around the other way, yeah. Okay. Yeah, that's good. It's for science. Do it again. Whoa, yeah.
Black and white. Then 10 years later, in 1984, my good friends Dave Vasquez and Craig Dawson came into my classroom and videotaped the course again. And 12 of those ended up as the tapes distributed by Addison Wesley. One of those I'd like to show you now features my good friend Paul Robinson, who turns out to be the author of the laboratory manual to the Conceptual Physics program. Let's drop in that class.
Don't touch it now. Don't touch it now. Okay, you'll be harmless if you touch it now. You can trust me. Okay. Okay. It's right on. Okay. Oh, that's beautiful. Stay holding it. Okay, look this way. Yeah, that's nice. Oh, that is nice. That's fantastic. Look. Oh, that's nice. That's nice. Very nice. Okay. Now, I tell you what. Could we all hold hands today? Yes. Okay. Yes. Let's all hold hands. Back here, John. Right, that's it. Right. Just come on. There we go. Come on. Okay. Dave, get that. Okay. Don't break the chain now. Anyone wearing pacemakers here? Okay. I hope not. If you're wearing a pacemaker, don't participate. Okay. Come on, here we go. It's okay, you back row types. Those are your neighbors you're sitting next to. Hold hands. It's all right. Okay, watch this gang. Inertia, huh? Card. Coin, huh? A body at rest tends to stay at rest. I'll show you a nice one. Here's the one shown to me by my friend Marshall Allenstein. Okay. Get a little hoop like this. Balance something on the top like this. Marshall Allenstein. Let's take this and let's show, by the way, this apple. And these as well. These are sharp nails, gang. Okay? About an inch apart. If you don't know what an inch is, think about 2.54 centimeters, about 2.54 centimeters apart, all right? And Paul is going to...
You sure these are not Teflon coated?
No, these are the real thing, honey.
You make this dead out about the
Do you know why we don't do it the other way around?
That's a good question.
This really is dangerous. And Paul's a little more foolish than I is. No. Paul's got more area. Ah, thank you, Norm. Okay. On your back, Robinson.
Oh, a day's work.
Yes. It's for science. Have to have Red Sox. Okay. Okay, you guys, protect yourself. Protect yourself. Yeah, okay. Okay. Here we go, gang. Here we go. Hurry. 1, 2. Oh, wait, I should tell you. I should tell you, this is not mind over matter. It's not what kind of granola or bean sprouts or meditation that Paul does. You know what this is all about, gang? Physics. Yeah. Okay, let's see it. Here we go. 1, 2, 3. Ha!
In 1989 and 1990, I took a leave from San Francisco and taught conceptual physics in Honolulu at the University of Hawaii. There, a small part of my class met in a TV studio classroom, and the whole course was videotaped, and that makes up the present series, which has been edited by my good friend Marshall Ellenstein. You'll notice in the series that the students are mainly first-year university students, but they could as well be first-year high school students. And you know why? Because the physics is the same. Let's drop in on opening lecture. Enjoy. Okay, gang, welcome to Conceptual Physics. Going to give you a lot of lectures this semester. And the lectures I'm giving are only the highlights of the course. Guess where the learning takes place? Reading the material and getting together with friends and talking about the ideas. So all I'm going to do is highlight some of the ideas and talk about physics. But the physics you'll learn from your textbook and working in groups and your laboratory. Now, first of all, what is physics? Today is a day not to take any notes, okay? Sometimes when something's important, I'll say, hey gang, put that in your notes, because you might need that later on, yeah? But for now, hang loose. What's physics? Let me ask you a question. Did you ever take a friend to a game, basketball game, sports game, any kind of game, and that friend doesn't know the rules of the game? And you're digging on the game, and you're really, really enjoying it. And you find out that the friend is kind of just sitting there looking, right? Can that friend appreciate the game if the friend doesn't know the rules? No. You gotta know the rules of the game before you can appreciate it. And guess what physics is, gang? It's the rules of the game of nature, the physical world. We're all in a physical world, which has surprisingly only a few rules. And those rules are what physics is about. And when we learn those rules, and we see how those rules apply to what's around us, then the physical world means more to us. And our position as a living being is elevated. And we can interact better with the physical world. It's like a couple of people walking through a park. One's a botanist, and the other's an everyday person like you and me. That botanist takes a 10-minute stroll through and sits down. That botanist sees all this stuff. You and I will walk through, boom, like that. I say to you, the botanist lives for a longer time than we do, because the botanist is alive to what's going on, and we don't notice it. And so you're going to find this course isn't something just to read in your book. This course is going to apply to you at home, not at home, everywhere you are. And you guys right now see physics as something that's between the pages of this book. I guarantee you, you're going to start to see it all around you. And that's why you like the course, I think. Now, once you learn the rules of the game, then it's nice to know how to keep score. And you can do that in the laboratory. So laboratories keeping score, and the lectures, what the rules are all about. Now, I'm not going to define physics more. All I'm going to do today is ask a bunch of questions. And these questions I want you to think about, and I'll tell you this. You might think you know the answers, and it turned out later on that maybe the answer you had was wrong. But I'll bet you this. By the end of the semester, you guys will be able to answer all these questions comfortably. Okay? Here's an example. I got a piece of clay and the keys. Clay's significantly heavier than the keys. When I drop them, they both fall together. Why didn't the clay fall faster? HC. How come? We're going to find out there's a reason for that. And we're going to find out that the fellow by the name of Galileo, who first did that, the Leaning Tower of Pisa, he was reported to have dropped a heavy, heavy ball and a light one. And boom, they both fell about together. And at that time, people thought that heavy things fell faster than light things. And Galileo demolished all of physics at that point by showing that, wow, it was wrong that heavy things fall faster than light things. That's only in the presence of air resistance. But without the air drag, both fall together. And Galileo couldn't answer the question why. And guess who's going to be able to answer that question why? Look at the person to the left of you. Look at the person to the right of you. Now look at yourself, gang, okay? Because we're all going to be knowing such a thing, huh? Why that's true. Why is it that a heavy rock will fall just as fast as a little pebble when air resistance is not so big to make a difference? Why? Hey, how does a rocket move? Rocket propelled in the sky. Is that physics? Rockets? You suppose rockets have to do with physics? What makes a rocket keep going? Is it something like this? You guys ever be in a swimming pool? You're in the pool and you get in the edge like this, and you kind of put your feet up and you push out like that. You kind of rocket across the pool. Does a rocket work a little bit like that? Check your neighbor. Answer begin with an N. It turns out, no, a rocket doesn't work like that. You know, when you push against the pool, you push out. What's a rocket pushing it against? Especially when it's above the air. What's it pushing against? What keeps it going? How does it work? B. We're going to be learning these things. Chapter 4. We say now, what goes up comes down. We don't really say that anymore. We used to say that before the 50s. What goes up comes down. Now, what goes up sometimes doesn't come down. And when it doesn't come down, and we call it, it begins with an S, ends with Adelaide. Try it. Go ahead, try it. Satellite, yay, okay? That's what a satellite is. Sometimes things don't come back down. How come? How many say, well, there's probably no reason for that. That's just a characteristic of satellites. Come on, gang. There's a reason for such a thing. And we're gonna, some people say, oh, it's beyond gravity. Guess what? Tilt, it's not beyond gravity. If the object were beyond gravity, you know what kind of path it would take? Anyone know that already? Let's suppose a satellite going around and around and around. All of a sudden, gravity cut off. Boom, what's the direction of the satellite going to be? Straight line, straight line, straight line. Just keep going, 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 going. But gravity pulls it into a curve. Why doesn't gravity crash it to the ground? HC. We're going to be learning that. That's chapter 4, too. You guys, when you're walking on a fence top, don't you put your arms out like this? Why do you put your arms out like that? Little kids say to you, hey, mister, it's you balancing on a fence. How come would you put your arms out? So I put my arms out like this, kid, help me balance better. Little kid says, well, I can see that. How come holding your arms out helps you balance better? And you say, you ever think about that? You guys know that's true. I wonder if there's a reason for such a thing. And it turns out that's chapter 7. Okay? If I take a rifle and I hold a rifle straight out, I mean straight, put a carpenter's level, honey, okay? And I hold like that, and I fire a bullet. That bullet gonna go straight out, yeah? And finally hit the ground, huh? Let's suppose when I do that, I drop a bullet from my hand. So one falls, and then goes straight out. Now watch this when I do it again. Which one hits the ground first? The one that's fired, or the one that drops? Take a guess and check your neighbor. Oh, how about this, gang? How about I go like this? I fire and I fire down, and I when I hit. When I fire down, let go. Which one hits the ground first? The one I fire or the one I drop? Try it. Begin with an F.
All right, let's suppose now I aim it up in the air like this. All right? And I fire. Bam! And when I pull the trigger, I drop one. Which one hits the ground first? The one that drops or the one that... Begin with a D. Try it. What is it? It's a drop. All right? Now let's suppose I go like this. Bam! Which one? Fire. All right, like this then, Lee.
Didn't drop.
Oh, I fire, and when I fire, I'd let one drop. No tricks. Which one hits the ground first?
The one that you fired.
Okay, how about like this? Bam.
The one that you fired because it's still ain't going
Yeah,
down.
how about like this, Lee?
The one that you dropped.
Ah, how about like this?
Down.
How about like this? How about like this?
That's hard to tell.
Can you see it's an even Steven? And so they both hit the ground same. Ain't that neat? We're going to talk more about that. You're driving a truck. You slam on the brakes. You just get to a stop. Now you're driving on the same truck, and you got it loaded up with 15 tons of pianos. You slam on the brakes. You skid to a stop. In which case do you skid further? You're in a roller skating rink. In a roller skating rink, you're skating around, and all of a sudden someone got a little piece of gum on the floor. You hit the gum, whip, boom, you fall down. You get up, you're okay, because you hit the wooden floor. Okay? Now you're outside, you're skating in the park. Okay? On the concrete. There's an acorn on the ground, right? You're skating by, whip, boom, you fall down. Honey, something called you over, and they have to get a medic for you. What's the difference? Why is it falling on the concrete? You get wiped out, you fall on the wooden floor, bounce a little bit, you're okay. Why? And you explain that to a little kid, and you tell a little kid, well, when you hit the wooden floor, honey, when you hit the wooden floor, it gives a little bit, it bends down. But when you hit that concrete, it doesn't give. It's like the difference between jumping out of a building into a net, which gives, and jumping onto the concrete sidewalk, which doesn't give. Which is better for you? Depending on the effect you want, okay? But then you could say to a little kid, hey, when you fall on the wooden floor, that little give, that helps you. And the little kid says, well, I know that. Why is it that when you fall on things with give, you don't get hurt? And when you fall on things that don't have give, you get hurt? HC. And you say, do you guys see what the physics, you getting the flavor? Sometimes physics takes simple questions and it finds out that the simple answers we have are only the beginning of an answer, and we got to go a little deeper. And that's what we're going to do. This whole course is all going to be common sense. Stuff you already know, but you're a little bit deeper. Oh, wow, it's a little bit more surprising because you're looking a little more carefully. We're not talking about weirdo stuff. We're talking about the physics of the everyday world, the stuff that's around you all the time. And all this stuff is going to start to make more sense to you. And you find that one thing links to another, and things connect in a beautiful way. And you can answer little questions like that. And then answering those bring new questions, which bring more interesting answers. And it keeps going and going and going. Then we'll talk about like electricity. We'll talk about sound, musical sounds. Electricity, 110 volts in your plug, huh? We'll have a great big Van de Graaff generator in here that'll be charged up to 1,000,000 volts. 1,000,000 volts. And you got 110 volts in your household circuit. If you take a couple of pieces of wire and stick them in your household circuit, that might be the last thing you ever do. But yet you can come up and you can touch that million volt generator, boom, high volt, and you're okay. HC. How can be? Similar to that, you guys know that if you reach in and you touch a hot pizza oven, you touch the hot oven, you're going to get burned if you touch the inside, right? But can you put your hand in the hot pizza oven in the air without getting burned for a moment? Yeah, you can do that. And it's just as hot as the side of the oven. Do you know that? Yeah. Do you guys know too that if you had a frying pan in there and it didn't have any handle and it had an iron handle and you reached in and that thing is like 400 degrees, you reach in and grab it, you know you're going to be hurt, right? But you do know if it's a wooden handle, you won't. You can touch the wood get the same temperature, but you can grab the wood and take it out quickly without burning your hand. And that's because wood is different than iron. Do you know what it is? Do you know what the property is that's different is? Have to do with heat, have to do with conduction. Put them together, we call it what? HC. Heat conduction, okay? And guess which has a poor heat conductivity? Wood or iron? Begin with a W. Try it, okay? And you know what? Even if the wood is hot, even if the wood is red hot. You know about these people that have these little courses and they charge you $300 and they teach you to walk barefoot in hot coals? Right? Mind over matter and the kind of noodles you eat and all that sort of thing. Mind thing. What is straight physics? That wood is a good insulator even when it's red hot. Why is that true? We'll be talking about that. Things like that. You guys know that, you know these little 4th of July sparklers? You see all that white stuff coming up, the white sparks? Do you know how hot those white sparks are? It's over 1,000 degrees. And you give this sparkler to a little kid, the little kid's holding it like that. Hi, 4th of July, honey. And these little sparks are bouncing all up the kid's face. That's like 1,000 degree sparks. How come those 1,000 degree sparks don't burn up the kid? Same reason when you touch that Van de Graaff generator, that 1,000,000 volts ain't going to burn you up either. And why is that true? We're going to talk about these ideas. We're going to talk about the idea how energy relates to these things. It's not only how hot, how much energy is going to flow. And we get that idea. We make these distinctions. You guys know when you go on the top of the mountains, it's cold up there. But you're closer to the sun, right? And at the top of the mountains, it's cold. And someone says, hey, how come it's so cold up here? So we're closer to the sun. Wait, no, that should make us hotter. You guys know when you're approaching the sun, it gets hotter and hotter, don't you? You be knowing that? I mean, you can get in the best ceramic materials that the humans can make. You get within 1,000,000 miles of that sun. Honey, you're going to fry to a crisp. 1,000,000 miles from the sun? Unless you go at nighttime. Hey, but the point, back again, you're up at the top of the hill, and it's cool up there. And you know what you can tell your friends? Hey gang, you know why it's so cool up here? Because warm air rises. Let me ask you a question. Does warm air rise? You guys know about that from before? You guys know that you get in the top of a ladder, you're painting the ceiling, it's a lot hotter up there than down below? Warm air does rise, okay? Why does warm air rise? Oh, there's probably no reason for that. It's just one of those things that happens, right? No. Warm air does rise, and when warm air rises, when a volume of warm air rises, is there more pressure, more air pressure up there, or less? When you're swimming in the water, and you're way, way, way down deep, more water pressure or less? More. Begin with an M. More, right? And as you come up, doesn't the pressure get less and less? Well, guess who lives in an ocean of air? Begin with you and with us. I mean, S. Us, we live in an ocean of air. And up there, there's not so much pressure. So let me ask you guys a question. What do you suppose would happen to the size of a balloon if you let it go and it floated higher and higher? Would the balloon get bigger or get squashed up smaller and smaller? Think about that and check your neighbor right now. So what do we think, gang? What's going to happen to the air? Is it going to expand or get compressed? Expand. When you take a tire pump and you compress the air, do you heat up the air or do you cool it off? You guys get practical experience in that? What happens when you compress air? Heat it or cool it or, I don't know. How many say, I don't know? Show of hands. How many say you heat it up? How about the opposite? If you expand some air, does it heat up or cool down? Would you like to have the answer to that? I could tell you the answer and you could put it in your notes. How about I show you the answer? Everybody take their hand and put it in front of their face, right or left, either one. Open your mouth and blow on it with your mouth open. Hottish or coolish? Okay, now that air didn't expand very much. Now do it again, and this time make your lips down small so the air has to expand when it comes out. Try it. Hey, what happened to the expanding air, gang? What did it do? Begin with a C or H? C. C, it cooled. How come the air cooled? That's chapter 17. Okay. You know how we answer a question like that? By thinking small. Really, really small. We think down to the little atoms. You guys know you're made out of atoms, don't you? I mean, not all of us, but most of us, right? Okay. Those who have the citizenship are made of atoms. No, come on. We're all made of little atoms. You guys know that? A lot of atoms or little atoms? Begin with an L. Try it. A lot of atoms. A lot or a lot? A lot. When you breathe in some air, atoms go in your lungs, right? Now when you breathe out, same atoms come out? Well, if that's the case, then why would you use chlorets, right? Can't a dog tell who you are by... Dog can tell even in the dark, yeah? When you breathe atoms out, you're breathing some of those atoms that are the molecules now, right? You guys know what a molecule is, right? Collection of atoms. And when you... Every time you breathe out, guess who's going outside? Guess yourself. Part of you is going out, Danny. A dog can pick it up, right? Even some... Harry's home, you know? Yeah, it turns out every time you breathe, you're breathing out part of you. Now, when you're breathing out part of you, there's a part of you going all up through. Someone comes by. Now, what do they got? Part of you. And that becomes part of them. So you are part of them. Are they part of you? Let's suppose you say, hey, I don't want anyone else to be a part of me. I want to be my own scene, right? You can't do it. Because every time you breathe in air, you're breathing atoms that were exhaled by someone else. Now, how many other people? We're going to be learning things like this. Hey, dig this. It turns out there are more atoms of gas in your air, in your lungs, than there are breaths of air in the whole atmosphere of the world. Almost the same ratio. Just about as many. 10 to the 22 in here, 10 to the 22 atoms. That's 10 with 22 zeros. And you got about 10 to the 22 breaths of air in the atmosphere. A little figuring out will tell you this. That if you took a breath of air and then wait 6 years so it's all spread out and go to some other part of the world and go, guess what you got? You got on the average one of those atoms that was in that one breath. Yeah? And there's many, many more breaths of air in your lungs than there were people that ever lived. People that ever lived about 10 to the 10th. So every time you take a breath, gang, you are breathing people who came before you, or even people that are alive 6 years ago on the other side of the world. So you know how these Buddhist types say, we are all one. We are all one, my children. What do the physics types say about that? It's true. It's true. We're all the same atom pool. Cycling. You want to do a short story sometime? Write about Johnny Atom or Julie Atom, okay? And how an atom goes from one place to another and goes da 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 da. And you know the atoms that make you up, guess how old they are? Older than the sun or younger than the sun? Older than the sun. The atoms that make you up were around before the sun came to be. How can be such a thing? And we talk about that. Kind of powerful. Then we're going to talk about color. See that's blue? See that's yellow? You see that's red? How come they're different colors? Somebody say, Hewitt, come on, we know that. We know that. There's a white light up above. The white light's all the colors mishmashed together. That's what white light is. Red, orange, yellow, blue, all smudged together, And all this is happening. The white light's coming down. This is just reflecting the blue part. This reflecting the red part. That's reflecting the yellow part. Big deal. We say, yeah, I know. We know that. Why does this reflect the blue part? Why doesn't this reflect the yellow part? And why does that reflect the yellow part? And why that the red part? Huh? What's going on? And to answer that, you got to get down at the atomic level. Why do things have colors? Why is the sky blue? Most of the time. How many people say, oh, there's no reason for the blue sky, honey. The skies just happen to be blue. That's the way it is. There's a reason for the sky being blue. You guys know that? And also, how about the red sunsets? The sunsets turn orange? Huh? You know what some people say at this point? Hewitt, off, man. Leave me alone. I don't want to know anything about little atoms making red sunsets. Leave me my sunsets. Some people think that if you explain the sunset, you're kind of spoiling it. You know what I'm saying? I don't want to know. I don't know about the little optical tuning forks and all that scattering and what's left. I don't want to know about that stuff. Which then can tell you why a cloud is white. And it tells you why the water is the color it is off of Hawaii here. Sort of that greenish blue. Why? Here's my bias, gang. To understand more about these things is to appreciate more about these things. Now that's a bias. That could be wrong. And that's individual. I'll give you an example. The person who appreciates music most is the person who understands music. who knows what to listen for. And I think, too, the person who can appreciate the world most is the person who understands most what's going on. What I'm going to be doing in this course is not telling you how beautiful the world is. I'm going to be telling you what to look for. And when you look for things, you'll see that, hey, there's a beauty that you wouldn't have noticed otherwise. So we're talking things like that. And then we're going to talk a little bit about nuclear physics, fission, fusion, radioactivity. What do you suppose makes the Earth hot? Volcanoes. Where's all that heat coming from? Would you believe it's nuclear power? Nuclear power under the ground? Would you believe it's radioactive decay? You know, if this were a piece of uranium, this piece of uranium would be a little bit warmer than anything else in the room. You know why? It's shooting out these little particles all the time, heating it up. And if I make it very, very enriched with uranium, it's going to be hotter, hotter, hotter. And guess what we get about the bottom of the world? So people that are afraid of radioactivity and nuclear power think it's something new that the human race has just come up with. Nuclear power has been around before the sun was here. That's what keeps the sun and the stars hot, and that's even what keeps the Earth hot. How come the Earth hasn't cooled off by now? Because there's radioactive decay happening underneath. And we're going to be talking about that. And that's particularly relevant here in Hawaii, because what do we got there? A hot spot. What makes that hot spot hot? What's fueling it? Is it like a carbon and oxygen combining? No. It's at the nuclear level. And most of everything we're going to talk about is going to be like physics of the everyday world like that, but we are going to get far out. And we're going to talk about the ideas of Albert Einstein, the ideas of relativity, what time it is on your clock, and how you move through space are related. Do you guys know that? We're all sitting at rest right now, and our clocks are running. We are advancing into the future at all the same rate. We're in the same space, and we all share the same time. But when I start to move, my watch is running differently than your watch. So long as I'm moving, it doesn't go at the same pace that yours is. Now, I'm only moving a little bit, and so the change is only a little bit. So little, there's no way that we have no instruments to measure the change for that kind of speed you saw. But if I start goosing that speed up faster and faster and faster, that difference in time becomes more apparent. You heard about the twin paradox? A couple of twins, one twin sitting over here, one sitting in a rocket ship, takes off, goes up, travels at speeds near the speed of light, comes back down, still young, and the other twin over here, decrepit. So the one that travels doesn't age as fast as the one that stays behind. Is that true or not? You give me the T. True. Take a piece of radioactive mineral, make it whirl round and round and round. Now measure it, and the decay rate goes down. Stop it, the same old decay rate. So when you're moving, the rate at which time travels changes.
So does that mean if you want to be young, you shouldn't do a lot of marathoning and stuff?
You notice I keep walking back and forth like this?
So you should never sit down.
Never sit down. Keep on trucking, honey. That's where it's at. Yeah.
So if you keep on running marathons all your life.
Marathons, you'll never age.
Really?
Now I'm kidding a little bit here, okay? The effect is so small that it's completely escaped the notice of the human race except one particular person. And that's a person who was thought to be a mental retard when he was a kid. That's a person that didn't talk till the age of 4. That's a person that took algebra in high school and couldn't hack it. Come on, some people can hack it, some people can't hack it. It's okay, you don't have to pass algebra. And he couldn't pass his algebra. Who am I talking about? In fact, he didn't even get a high school diploma.
You did?
No. Then he went to take the entrance exams to get into the Polytechnic Institute. And guess what he did? Begin with a F, L, U. He flunked. That's okay. Some people pass, some people flunk. Don't make a big deal of it. Then he met someone, got him entry, he tried it again, and this time he passed. And he did very, very well in school, it turns out, and we're talking about who? Albert Einstein. Some people's time is a little bit different than other people's time. Some of you people sitting in the class right now, it's the wrong time for you to be here. It really is. Maybe a little bit down the road, all the stuff we're going to talk about will more resonate with where you are. Sometimes information comes in at a time when you're not ready for it. That's kind of a shame. And sometimes it comes at just the right time. And information comes in when you're ready for it, and you grow, you grow, you grow. It's like watering a plant. You got to water the plant at the right time. And here we are all in class, and we're going to all learn physics together. And I hope for all of us it's what? It's the right, the right time. This is the time to learn about the physical world. I want you all to do something between now and next time. We're all going to look at chapter 2. We're going to be reading about it. We're going to be reading about motion, moving things, accelerating things, falling things. And we read about that, and next time we'll talk about it and kind of pull it all together. Okay? Catch you next time. Physics.